to do some algebraic manipulations on it. So, but first thing I want to talk about is finding asymptotes. So they're not always going to be as easy as the part one. I mean, some of them could look very easily like that, but some of them, the ones in this section toward the end of the homework today, will get a little bit more complicated. So here's the quickest and easiest way to find your asymptotes. So to find vertical asymptotes, it's really easy to find vertical asymptotes. All you do is set the denominator equal to 0. Because you don't want 0 in a denominator. So I know it seems weird, then why do we set it equal to 0? Because that's where the asymptote would be. That's where there would be a problem at. So take your denominator, set it equal to 0 is probably the best and quickest thing to find those asymptotes quickly. Horizontal asymptote, on the other hand, is a little bit tricky. There's 3 different types of horizontal asymptotes that could occur. So to find horizontal asymptotes, there's 3 choices. Okay, so choice number 1, and it's based off of the degree of the polynomial on top versus the degree on the bottom. Remember, degree refers to the exponent. So if the degree on top is less than the degree on the bottom, then this is always, always, always your horizontal asymptote. Y equals 0, always. If the top degree is less than the bottom, your horizontal asymptote is 0, no matter what. Well, what happens if the degree on top is equal to the degree on the bottom? Well, then your horizontal asymptote is equal to the coefficients of the degrees. And I'll explain what that means when we do a problem. It's pretty easy to see it. You'll see it. It's not too hard. So obviously there's a third choice. The top less than the bottom, it's 0. The top equal to the bottom, it's the coefficients in front. If the degree is greater than. If the degree is greater than the one on the bottom, then there is no horizontal asymptote. However, you're like, oh, yay. However, there could be a part C. If the degree on top is bigger than the degree on bottom by 1 degree, meaning, let's say on top I had an x cubed polynomial and then on bottom I had an x squared. That would be by 1 degree. Okay, that would have no horizontal asymptote, but it could have this asymptote. It's called you could have a slant asymptote, also known as an oblique asymptote. Every book is different, calls them all the different things. Slant asymptote or an oblique asymptote. And to find that equation for that slant asymptote, you have to use long division and write it as y equals mx plus b. It's not that hard. I know this seems like a lot, but honestly, when you see us do the problems, they all come out to be pretty neat. But those are your 3 choices for horizontal asymptote. You could be 0, you'd be the coefficients, you could have none, If you're higher on top by the bottom by 1, though, you have a slant asymptote, and we have to figure out the slant equation. And that'll be probably, I think, my last equation, my last example I'll do tonight. So let's do an example of this so you can see it's not terrible. Let's graph f of x equals 2x plus 1 over x minus 3. And you have to tonight find the horizontal asymptote, find the vertical asymptote, and the domain. You know, good old stuff that we love to do. So again, you are more than welcome to double check yourself and plug this into the calculator. By all means, do so, okay? But let me just show you how you can solve this all algebraically. It's not too hard. So the first thing I start with is the vertical. That's why I put it up here at letter A. So vertical asymptote, set the denominator equal to 0. Perfect. Let's do that. Let's take our denominator, x minus 3. Let's set it equal to 0. X equals 3. There's your vertical asymptote. Boom, done. Perfect. Let's find the horizontal asymptote. Horizontal asymptote has 3 choices. It's going to either be 0, it's the coefficients of the degree, or it's none. There isn't there. So it's based off of the degree on top and degree on bottom. So the degree on top right now is a degree 1, or it's linear. On the bottom, it's a degree 1. Oh, so the degree on top is equal to the degree on the bottom. So what does that mean? It means it's the coefficients of the degrees. It's these coefficients. There's a 2 here. What's right here? A 1. 2 over 1. Y equals 2. That's the coefficients because the degrees are equal. Easy peasy. So let's graph this. I'm going to have a vertical asymptote at x equals 3. 1, 2, 3. Dot, 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 dot. X equals 3. And a horizontal asymptote at 1, 2. And you put a hook here. And you put a hook here. And now let's state the domain. The domain is up to the x equal 3, the vertical line, that because our domain is how wide, so it's this one right here. So it's going to go from negative infinity up to vertical asymptote at 3, united with 3 to infinity. So there's your 3 answers for that. No problem. Let's do another one. You got to do a couple of these to feel like you got a knack for them. And again, by all means, put it in your calculator. Double check. Make sure you have it all written correctly and graphed correctly. But you have the algebra skills to do this. So f of x equals x plus 1 on top and 2x squared plus 5x minus 3. And we're going to do the same thing. We're going to find the vertical, horizontal, and domain. Okay, so I did this one on purpose because I want to make sure we know how to factor. I was reprimanding my calculus students today because they still don't know how to factor. So it gets me upset. Vertical asymptote. You set the bottom equal to 0. Okay, so I need to factor this. This is a trinomial. This is a trinomial with a coefficient of 2. I have to multiply these together. What multiplies to -6, 2 times -3 is -6, but adds to a 5. This is how I do it. So the two numbers that multiply to -6 but add to -5 would be Why am I not thinking right now? Negative 6, I'm sorry, positive 6 and negative 1. Yeah, there we go. Positive 6 and negative 1, right? 6 times negative 1 is negative 6. Positive 6 and negative 1 add together to be 5. Now, here's the thing. When you have a coefficient in front of your x squared, you divide that one and that one by it, the number by it. If it reduces, then reduce it. So like 6 over 2 reduces to x plus 3. If it doesn't, you slide this one up. You bottom it up. So we call it 2x minus 1. Okay? So what does that mean? Well, that means I actually have 2, and this is allowed, 2 vertical asymptotes. Set this one equal to 0 and this equal to 0. So I have a vertical asymptote at negative 3 and at 1/2. Woo! Negative 3 and 1/2. All right, so we know that's where the vertical asymptote is. Part 2, where's the horizontal asymptote? Well, the horizontal asymptote is based on degrees. And again, you have 3 choices. Choice 1, it's going to be 0. Choice 2, it's going to be the coefficients. Choice 3, it's going to be none. So let's look. Degree on top is 1. Degree on bottom is 2. Since the top is smaller than the bottom, since the degree on top is less than the degree on the bottom, again, let's look at our notes. That's why we take them. Degree on top, less than degree on bottom. This is always my horizontal asymptote, y equals 0. All right, so let's graph this. Let's see what this looks like. This is going to be really, really interesting. So you have 2 vertical asymptotes at negative 3. X equals negative 3. And then you have another one at 1/2, which would be like, if here's 1, 1/2 would be like right there. And then you have a horizontal asymptote at 0, so that doesn't change. But your picture is going to look different. And I want to show you it on good old Mr. Desmos. Let me see. Because you don't just have 2 hooks anymore. You have this extra thing going on. I mean, look, you don't just have a 1, 2, 3. You have 1, 2, 3, 4, 5, 6 parts. So thankfully, you get to use this beautiful thing right here, and or a calculator. So x plus 1 divided by 2x squared plus 5x minus 3. Ooh, look at this. So notice what you have here. You have your 1 hook right here. Notice how close I am to that. Let's see if I can zoom in a little bit. Yeah, there we go. Here's 2. Here's 1. So I'm reaching 1/2 asymptote. Then I've got this like almost like this cubic dance right here in the middle. And then here's my other hook. So I have a hook here. I have this cubic thing happening in the middle here. And then I have the other hook up here. And now if I asked you what's the domain of this, remember domain is up to those vertical asymptotes where there's 2 of them. So you have to write them all. So you'd say I'm good from negative infinity up to my first vertical asymptote, which is negative 3. United with, and then you repeat it again, negative 3 to my next vertical asymptote at 1/2. United with, and then you repeat it again, and then I'm good from 1/2 to infinity. That would be your domain. So, interesting question right there. It has 2. Can you have 2 vertical asymptotes? Sure can. You sure can. All right. But there's always different ones here. I mean, I'm trying to show you all the different kinds you could get. Graph this one. And I'm interested to see what Desmos does because I can tell you what the calculator does on this one. It's actually very hard to see what this calculator does on this one. Okay. When you have a polynomial equal to a polynomial, like a polynomials that are factorable, let me say that, excuse me, like you should know that the x squared minus 1 factors, and you should know that x squared minus x minus 2 also factors. You need to factor it first. So factor everything first. Factor, factor, factor. Here's why. If your factors cancel, move this up here for a second so you can see. If your factors cancel, then you have a hole in the graph. And that's why I said I'm interested to see how Desmos does it. In the calculator, you cannot tell it's a hole. You cannot tell there's a hole there. If your factor doesn't cancel in the denominator, like if you still have a denominator factor left over, it's an asymptote. So if there is a factor left in the denominator, it's an asymptote. Very, very important. Very also important when you take calculus to understand this idea of when's it a hole, when's it an asymptote. We actually changed the name in calculus. We now call it removable and non-removable, which is kind of weird that that's exactly what I was teaching about today. But let's factor this. Let's factor the top. X squared minus 1 is a difference of two squares. So you write that as x plus 1, x minus 1. Because if you FOIL that back out, the middles would cancel and you'd just be left with x squared minus 1. This one, you're saying, okay, what multiplies to -2 but adds to 1? Multiplies to -2 but adds to 1 would be -2 and +1. And you don't have to do that divide by anything because what would you divide by? 1? It doesn't make a difference. Now look what happens here. They cancel. Uh-oh. What does that mean? That means you have a hole in the graph. And where is that hole located at? So let's write this down. There is a hole in the graph at x plus 1 equal to 0 or x equal to -1. There's a hole at -1. There's actually like a circle that you would draw. Now, the vertical asymptote then would be the factor that's left in the denominator. That's the asymptote, okay? Not the hole. So there's a vertical asymptote only at x equals +2. Set that equal to 0. That's the only one. There's only one vertical asymptote at x equals 2. So that's the new thing you have to learn about that. And like I said, we're going to look to see what this looks like in a moment. Horizontal asymptote, remember that's based on the degrees. So let's check out the degrees on top. The degree is 2. Degree on the bottom is 2. If they're equal, get your notes, turn over. If they're equal, it's the coefficients of those degrees. Well, the coefficient in front here is a 1 and this is a 1, so it's 1 over 1. So y equals 1. So when I go to graph this, I would have a vertical asymptote at x equals 2. And a horizontal asymptote at 1. And I have a hook here and a hook here. However, let's see if I can change my color on this one. At x equals -1, I have a hole in my graph. Now, like I said, I'm kind of interested to see. I know what the calculator does. The calculator won't show you that hole. It'll look just like a hook and a hook. So I'm kind of interested to see what Desmos does. So bear with me as I go to Desmos and see if it's superior. It might be superior, and then I'll have to cave to the superiority of it, but x squared minus 1 on top divided by x squared minus x minus 2. Is it giving me a hole? It's not giving me a hole. Ah, it is not superior. Wow, it's giving me an x-intercept and a y-intercept, but at -1, it's defining it. It's not. Oh, I saw it. Oh, I saw it right there for a second. But it won't keep it there. I don't know if you can see me pressing on it. It says -1 undefined. There is a hole in the graph, and notice it makes an open circle. All right, kind of legit. Because in order to see that on the calculator, you have to go to the table, and the table says error in it. So impressive. I bow to your superiority, Desmos. You are amazing. Now, what does that mean for domain? Real quick. The domain for this one, that hole is going to be a problem still. That it's still just like, it's almost still like a double asymptote problem. So you would say from -infinity up until that hole, which was at -1. And then from -1, ooh, getting updates. Thanks, remind me later. Ugh, come on now. Sorry about that. So -infinity to -1 united with -1 to, where's my next problem? Here's my asymptote 2. United with 2 to infinity. So that, I still include the hole in the domain, and I include the vertical asymptote for that one also, okay? So what's the whole big idea of this problem? Factor. If it crosses off, it's a hole. If it doesn't cross off in the denominator is that asymptote. And then you write out your lovely thing. All right, 3 more examples. We're doing good. We got this. We are going to graph f of x equals x squared minus 16 over x minus 4. Oh, there it is again. Factor. Oy, oy, oy. Factor. Please. All right, so let's see. Factor x squared minus 16 would be x plus 4, x minus 4. Oh, I can cross off, which means I'm a hole in the graph at, set that factor that crossed off, x minus 4, set it equal to 0. So there's a hole in the graph at 4. There's a hole in the graph at 4. Now, what just also happened was, notice something. I don't have a vertical asymptote anymore. I don't have anything in the bottom now. They crossed off. I have a 1, it's over 1. Everything's over 1. I don't have a factor left in the bottom, so I have no vertical asymptote. Can that happen? There is no, well, there's none. There's no vertical asymptote. What about the horizontal asymptote? Well, it crossed off, so I don't really even have a horizontal asymptote. What ends up happening is what you're left with, this thing that didn't cross off, which is in the numerator, is really what you graph. You graph the x plus 4 line. So 1, 2, 3, 4, and you go up 1 over 1. Let's see, up 1 over 1, up 1 over 1. But there's a hole in the graph at 4. 1, 2, 3, 4. There is a hole right there in that graph. So again, let's look at the superiority here of Desmos, x squared. Oops, didn't mean to do that. X squared minus 16 divided by x minus 4. Okay, well, let's go out a little bit here. Look, it looks just like a straight line. It looks just like the x plus 4 line because the factors canceled. And let's see if we can, move our cursor. Here's 4. So I'm going to try to see if I can just move it. Oh, I saw it. There it is. 4, undefined. There's a hole in the graph right there at 4. And again, if it cancels, it's a hole in the graph. So again, big idea, please, please, please. Factor, factor, factor. Graph f of x equals negative 4x squared over x to the 4th plus 1. Interesting. I like doing this problem because I think everybody doesn't think that this can happen, but and I don't know if you noticed me, I start my problems, all of them the same. I start doing vertical asymptote. That's the first thing I do. So I go to my denominator and I set it equal. I write VA, vertical asymptote. I take my denominator, x to the 4th plus 1. I set it equal to 0. And I go to solve it. X to the 4th equals negative 1. Can that happen? Can you get negative 1? Can you take the 4th root of negative 1? Are you going to get i's? No. This can't happen. There is no vertical asymptote. That can end up happening. There's never a time where this bottom denominator is going to be 0, ever. Even if x was negative 1, negative 1 to the 4th would be 1. 1 plus 1 is 2. Even if, x was 10 to the, it's never, even if it was 0, 0 to the 4th is 0, plus 1 is 1. You're never going to get a 0 in the bottom. So there's no vertical asymptote. What about horizontal asymptote? Horizontal asymptote is based on degrees. So the degree on top is 2. The degree on the bottom is 4. The degree on top is less than the degree on the bottom. So this one is y equals 0. But this one looks a little strange because I got this x to the 4th and x. I don't really have a parent function here. So you're going to want to, I want to graph this. So let's type negative 4x squared. So I know it's going to flip over the x-axis divided by x to the 4th plus 1. Oh. Ooh, look at this graph. This is kind of neat, this weird like W shape. Okay, look at that. You have that horizontal asymptote at 0. That's happening. Please zoom in. Okay, you have some max and mins here. Well, you have some mins, absolute mins right there. You get a relative max. No, actually it would be the absolute max at 0, 0. Your x and y intercept would be right there. So pretty neat. This is even symmetry, if you remember what that means, that you flip over the y-axis. So just a couple things to look here. So let's go back and draw this out on our little graph right here. So it kind of looks something like this. That's terrible, but it works. So if I asked you what was the domain of this picture, from how wide was this thing getting? Let's just say domain, maybe they'll ask you a domain. How wide is this thing getting? Well, there's no problems here. I don't have any vertical asymptotes. I'm good. I'm going from negative infinity to infinity. And this has even symmetry. I want you to write that down. I think I wrote it down for a reason because I'm wondering if they're going to ask it to you in homework tonight. Even symmetry flips over the y-axis. This piece right here, if I flip it over this y-axis, it would look the same on that side. Okay, I wrote it in my notes for some reason. Last two examples, and we're done. Hopefully this is making sense. Again, you get a lot. You get the calculator and all that fun stuff tonight. Oh, this is a different question. That's right. They gave this to you. Let's do this one. So I saw this on homework. It says use the table to find P and Q in the form f of x equals x minus P over x minus Q. And then they give you this table. 0.5, 1.3333. This is the table they're giving you. 2, 0, 3, -1, 4, error, and 5, 3. So use the table to find P and Q in the form of f of x equals x minus P over x minus Q. You'll have a question just like this. So here's what we know. We are not allowed 0 in the denominator. Your bottom cannot equal 0. If it does, then you would have a problem. You would have an asymptote. Your calculator or your table of values would say error. Hint, hint, hint. It would say error at that point. I have an error in my graph. In the table they gave me. So that means I know that this right here must be my Q. My Q must be 4. Right? This would, if it was x minus 4 in the bottom, I would have 4 would be an asymptote. I would get the answer error for my y value, undefined. Undefined is what it says on Desmos. All right, so then what's my P going to be based off of these? The P going to be? Well, your P is allowed to be 0. Your top equation is allowed to be 0. So that's actually going to give us a clue here. We are allowed to set that equal to 0, to find a 0. And this right here is a 0. So this would be our top. Our top would be x minus 2. That would be my function. So my P would be 2, and my Q would be 4. I thought that was a weird way of doing it, but you can look it up yourself. You can type into the calculator x minus 2. I mean, just to double check. It's never hard to double check. It's always a good idea. X minus 2 divided by x minus 4. Let's go to the table. Let me see. I just want to make sure the table's starting. And look at that. Here's 0.5. Here's 1.33. Here's 2, 0. Here's 3. Here's 4, error. Okay. I got the same exact table that they gave me. So I must have done it right. But the trick to that is if you see error, that would go in the bottom. That would probably be an asymptote. And then your 0 would be on top. Your 0, your x-intercept would be from the top. All right, one more question. One more question. And this is on slant asymptotes. This is what we were talking briefly about in the beginning of class. So just to refresh your memory, we are going to, here's our last example. Let's see. We are going to graph f of x equals x squared plus 1 over x minus 2. Find all asymptotes and state the domain, because we love to do that. All right. And I've already given you a hint. This one's going to have a slant asymptote. I'm going to show you why it's going to have a slant asymptote. So first rule, I would say factor everything. X squared plus 1 cannot be factored. If you didn't know that, you should. If it was x squared minus 1, that's factorable, but that's not going to do anything anyway. But factor so that way you make sure you know where all the holes are. So step number 1, I always do vertical asymptote first. Vertical asymptote, take that bottom, set it equal to 0. X is 2. We got a vertical asymptote. Okay, we got this one so that we know it. All right, horizontal asymptote. Go there. Horizontal asymptote is based on degree. Degree on top is 2. Degree on bottom is 1. The top is bigger than the bottom. Well, again, going back to my notes, if the top is bigger than the bottom, I do not have a horizontal asymptote. So yay, there's none. But wait, if the degree on top is bigger by the degree on the bottom by 1 degree, you have a slant or an oblique asymptote. And you have to find that oblique asymptote in the form of y equals mx plus b. So we have a degree on top bigger than degree on bottom by 1. So yes, we have a slant asymptote. How do we find that slant asymptote? We have to do long division. Okay, you could probably do synthetic division, but sometimes this might be like x cubed and this would be x squared, and you wouldn't be able to do synthetic on that. So just might get into a habit of doing long division now. I'll show you how to do this one synthetically in a minute, but so pretty much you take your bottom x minus 2 and we're going to long divide it into x squared. I don't have an x term, so I'm going to have to put 0x and then plus 1. It's not that hard, honestly, because all you need it to be is in the form of y equals mx plus b. Mx plus b, literally 2 terms. That's all as far as you have to go. You don't have to get a remainder. You don't have to do anything. Here's what I mean. Look at this first term. Look at this first term. How does an x become an x squared? Multiply by what? Multiply by x. Take this x and multiply it to this whole thing. X times x, x squared. X times 2 minus 2x. Then you have to subtract. So change the sign. This first term will cancel. You'll be left with 2x. Drop down and do it again. How does this x become a 2x now? Well, you would need a 2, a positive 2. And you don't have to go any further right now. Don't go any further. Why? Because I am in the form of y equals mx plus b. Done. So what does this mean? This is pretty cool. I mean, I'm a math teacher. I think these things are cool. But so here's what you have. And again, I'll show you on Desmos in a minute. So you have this vertical asymptote at x equals 2. X equals 2. You don't have a horizontal asymptote at all, but you have this slant asymptote, and it's running across the linear line x plus 2, meaning, so here's 1, 2. So it's going up 1 over 1, up 1 over 1. So there is a slant here. This is y equals mx plus b. Now, your hooks, normally they lie they make a hook in quadrant 1 and quadrant 2. Well, now you actually have, you've slanted the x and y axes. So now you actually end up with a hook up here and a hook down here. And I mean, that's pretty cool. So we're going to look at it right now just to double check it, to see that we did it graph. So you have x squared plus 1 divided by x minus 2. Ooh, I can see the 1 curve. Let me see if I got, look at that. And not only that, I'm actually going to put my slant asymptote right here. So I want to see y equals mx plus b. So what was it? X plus 2. Look at that. Look at that line right there. X equals 2 is my slant. See that purple line? And I'm even going to put my vertical asymptote. Let's see, what's that? X equals 2. And then look at that. I did it on the money. And that hook is now inside. That's what happens with a slant asymptote. Now, how do I do the domain? Well, your domain, remember, these still are going here out. The hooks are going. So you're good from negative infinity up till that vertical asymptote. Negative infinity up until 2, united with 2 to infinity. The hardest part is going to be this slant asymptote, but it's not that hard. You can stop the equation after long division. I do want to do synthetic division because this one you can. Like I said, if you had an x squared minus 2, you wouldn't be able to do synthetic division. But if I did synthetic division real quick, I would divide by 2. I would have a 1, a 0, a 1. I'd drop that down, 2, drop that down. And you don't even have to go further because this is mx plus b. So it's very easy if it was square. If this was an x minus 2 or an x minus k form, then you could easily find that. Hopefully it is like that on homework tonight. Well, that's it, y'all. Hopefully you're impressed as I am about these lovely functions, these rational functions. They're kind of neat. All right, so here's what we got. What do we got? You can easily stay online and get that homework done. Please don't waste this time. I get very frustrated because I'm giving you this time and I want you to use it and ask me questions if you need, or at least get homework number 14 done right now because we just went over it all. It's fresh in your brain. Get it done, and then come back on Thursday night. We'll do 5.3. That might take a little bit of time, but. All right, unless you have anything else, you are free to go and do the homework. I'll be here, and let me know if you have any questions. What are you doing, crazy? You are crazy.